Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 31 on complex areas.
Computing areas by means of a definite integral is one of the classical applications of calculus, but it's not always so straightforward. Some shapes are too complex to be easily decomposed into triangles or rectangles. This is especially true in the context of applications where simplicity must yield to reality. In this lesson, we'll learn how to handle some of those problems by using the area element.
We begin this lesson with a quick, classical example of computing the area between two curves, y minus x equals 0 and y squared plus x equals 2. The first of these is the diagonal line of slope 1. The second is a parabola that opens to the left. We need to compute the area of the region between them. I'll leave it to you to do the substitution and algebra to determine the intersection points at 1, 1 and -2, -2. And now, to compute the area, we could proceed as before by sweeping out with a vertical strip as an area element. But if we do this, then we need to decompose the region into two different parts. The area element is, on the first part, as x goes from -2 to 1, the difference in height. We need to solve for the y-coordinates. In doing so, we can write the area element as the top, y equals x, minus negative square root of 2 minus x. This height is multiplied by the width, dx. For the right-hand side of this region, as x is going from 1 to 2, then the area element is twice square root of 2 minus x times dx. And to compute the area, we need to integrate this area element. That means we're going to have to write down a pair of integrals. The integral, as x goes from -2 to 1, of x plus root 2 minus x dx, plus the integral, as x goes from 1 to 2, of twice root 2 minus x dx. Now, neither of these is a terribly difficult integral, but we're not going to do it. Why? Because there is a simpler method. We're going to reverse the direction of integration and integrate with respect to y instead of with respect to x. And so, solving for the x coordinates and sweeping out via a horizontal strip as our area element, we see there is a uniform area element, and it will reduce to a single integral. What is this area element? If we take the x-coordinate on the right, that's 2 minus y squared, subtract the x-coordinate on the left, namely y, multiplied by the thickness, dy, then we can integrate this area element as y goes from -2 to 1. This is a much simpler integral, and we get simply 2y minus y cubed over 3 minus y squared over 2, evaluated from -2 to 1. That equals 9/2, the area. The direction matters. If you encounter an integral that is too difficult, try reversing the direction. A related, albeit more complex example comes to us from thermodynamics in the analysis of an idealized heat engine. What happens to a gas in a chamber in something that, say, might power an automobile? Now, we're going to go over a couple of terms from thermodynamics very quickly. All of these have to do with measuring what is happening to the volume, V, and the pressure, P, of the gas in the chamber. In this idealized heat engine, there are 4 stages or strokes. The first is called a combustion stage, otherwise known as an isothermal expansion. The volume is increasing, and the pressure, P, times the volume, V, is constant. Let's call that A. So in this first stroke, you're moving to the right along a curve in the VP plane, where the product is a constant. The second stroke is the power stroke, sometimes called an isentropic expansion. In this case, you're moving along the curve. P times V to the gamma equals another constant, let's say B. Here, gamma is yet another constant that is greater than 1 and depends upon the properties of the gas. The third stroke or stage is the exhaust stroke. This is an isothermal contraction in which V is decreasing, and you're moving along a curve. P times V equals another constant. Let's call this one A sub 0, and we'll call the former PV constant A sub 1. Now we're moving to the left along one of these curves. The last stroke is the compression stroke, otherwise known as an isentropic contraction. Volume is decreasing, and you move along the curve. P, V to the gamma, equals a constant. We'll call this fourth constant B naught, replacing the B in our earlier isentropic expansion with B1. All right, that's a lot of setup. What's the payoff here? In thermodynamics, you trace out this region in the VP plane, and the work that the engine does over 4 strokes of a cycle is equal to the area that is traced out in this plane. And so we are motivated to find that area. If we sweep out this region, integrating with respect to V using vertical strips, it's not so simple. It seems to have several different pieces. Perhaps reversing the direction would help? No, this does not make things any simpler at all. So let's go back to integrating with respect to V. In this case, the region breaks up into 3 distinct zones, each requiring its own integral. In the first piece, we have on the top the curve PV equals A1. Solving for P gives us A1 over V. Subtracting the P value for the bottom curve means subtracting B naught over V to the gamma. That's for the first region. The second region is between 2 isothermal curves. And that gives us A1 minus A naught over V. The third region, with a little bit of work, gives us an integrand of B1 over V to the gamma minus A naught over V. Now, none of these integrals is difficult to perform. What is difficult is determining the limits of integration, because we have to find all 4 intersection points of these curves and determine their V values. I'll leave it to you to show, with not a small amount of work, that the first intersection point on the left is quantity B naught over A1 raised to the power 1 minus gamma. You can imagine how much work it's going to take to do and simplify these integrals. That's the bad news. The good news is that the answer at the end is really quite simple. A1 minus A naught over gamma minus 1 times log of B1 over B naught. If the answer is that simple, well, isn't there an easier way to do the integral? There is, but you're going to have to wait to find out. Complicated shapes require new techniques. Here's one approach. In the case where a shape is defined by a radial distance, we can use what is called polar coordinates. So if we have a shape of the form r equals f of theta, where r is a distance to the origin, theta is an angle made to the x-axis, then trying to fill out such a region by vertical or horizontal strips as an area element is likely to lead to frustration. And so, as we did in the case of a circular disk, we can use an angular wedge and sweep that around based at the origin. What will this area element look like? We'll approximate it as a triangle whose length is r, the radial distance, and whose height is r times d theta. In this case, the area element is the area of this triangle, 1/2 r times r d theta. And that is 1/2 r squared d theta, but remember r is given as a function, f of theta. Hence, we have something that we can integrate to get the area, that being the integral of 1/2 quantity f of theta squared d theta. Let's explore this in the context of an example. Compute the area between the regions r less than or equal to 2 sine theta and r greater than or equal to 1. We can clearly see that r equals 1 is a circle, radius 1, centered at the origin. I'll leave it to you to discover that r equals 2 sine theta is likewise a circle of radius 1 shifted up the y-axis. These curves intersect at 2 points. What are they? Well, by setting the r values equal and solving for theta, we see that these points are at theta equals pi over 6 and 5 pi over 6. And now we want to compute the area of the region between the one and the other by sweeping out with a angular wedge. This area element is going to look like the difference between two triangles centered at the origin. The area element, dA, in this case, is going to be what? Well, we take the outer area element, that is 1/2 of the outer radius squared, and subtract off 1/2 times the inner radius squared. Of course, the outer radius is r equals 2 sine theta. The inner radius is r equals 1. Paying careful attention to our inequalities. We have to perform this integration as theta goes from pi over 6 to 5 pi over 6. And so we see that with a little bit of simplification using the double angle formula, we can reduce this integral to 1 minus cosine 2 theta minus 1/2 d theta. Simplifying a little bit, we can integrate negative cosine 2 theta to minus 1/2 sine 2 theta, and the 1/2 becomes 1/2 theta. Evaluating this from pi over 6 to 5 pi over 6 gives us, with work, our answer, pi over 3 plus square root of 3 over 2. Now, these examples, though complicated, illustrate a deeper truth, namely that by changing coordinates, we can make the integral simpler. It looks like we're playing around with triangles and area elements like that, but what we're really doing is changing coordinates so that we can integrate with respect to theta. Likewise, in the problem that we didn't solve about thermodynamics, the right way to solve that problem is to change to a new coordinate system in which the associated shape becomes a rectangle. That will make things easier to handle. You're going to have to wait until you get to multivariable calculus to see how to do this properly.
Through solving, or at least attempting, some more challenging problems, we're led to a new perspective that of a change of variables formula for planar, two-dimensional shapes. We're going to save the full exposition of those ideas for multivariable calculus, but if you'd like to see a preview, check out the bonus material. Then, we'll move on to our next lesson, where we'll compute volumes.